From the very first time humans looked up at the night sky, the stars have fascinated us. They were more than just distant points of light. They were mysteries, challenges, and destinations. Long before rockets, astronauts, or space stations, civilizations across the world studied the heavens. Ancient Egyptians built massive structures like pyramids aligned with stars. The Mayans charted the movement of planets with astonishing accuracy. The Babylonians recorded celestial events that we still study today. All these efforts shared a common goal: understanding our place in the universe. For thousands of years, space was a realm of myths and imagination. We imagined gods riding across the skies in chariots, or monsters hiding behind the moon. But the desire to reach beyond our planet was already forming. The first step wasn't with rockets, it was with mathematics, observation, and imagination. Astronomers like Nicolaus Copernicus proposed that Earth wasn't the center of the universe. Galileo Galilei, using one of the earliest telescopes, discovered moons around Jupiter. These discoveries challenged centuries of thinking and set humanity on a path toward exploring the cosmos. By the 20th century, the dream of spaceflight was no longer just philosophical, it became scientific and technical. Visionaries like Konstantin Tsiolkovsky in Russia and Robert Goddard in America began to design the first rockets. They understood that to escape Earth's gravity, humans would need incredible speed and power. These early pioneers faced immense skepticism, yet they laid the groundwork for what would become one of the most daring chapters of human history. The tension between nations also played a role. After World War II, the world found itself in a new kind of competition: the Cold War. The United States and the Soviet Union were not only vying for military and technological dominance but also for achievements in space. This rivalry turned space from a dream into a race. In 1957, the Soviet Union launched Sputnik, the first artificial satellite, into orbit. Suddenly, the reality of space was no longer just a theory, it was something humans could reach. Sputnik wasn't large, it was small, but it carried enormous significance. It was the first human-made object to circle the Earth, sending radio signals back and proving that humanity could enter the final frontier. The launch of Sputnik shocked the world. In the United States, it sparked what came to be known as the space race. Scientists, engineers, and ordinary citizens were captivated by the possibilities. What could humans achieve if we dared to venture further? This era of discovery combined daring scientific experimentation with the imagination of a generation that had grown up gazing at the stars. The stage was set for the missions that would define space exploration for decades to come. After Sputnik, the world watched closely as the Soviet Union launched the first living passenger into orbit, a dog named Laika. While the mission was brief, and Laika did not survive, it marked the first time a living creature had endured spaceflight. This experiment was terrifying and inspiring at the same time. Scientists learned valuable information about the effects of weightlessness, radiation, and confinement on living beings. The mission also showed humanity that space was no longer a distant dream, it was a place where life itself could travel, at least for a time. The United States quickly responded. In 1961, President John F. Kennedy made a historic announcement: America would commit itself to sending a human to the moon and returning him safely to Earth before the end of the decade. This was more than a scientific challenge, it was a statement of vision, ambition, and determination. The announcement ignited imagination across the nation. Schools, universities, and research institutions mobilized. Young people who had never considered careers in science suddenly wanted to become engineers, astronauts, or technicians. Kennedy's words were not just about a mission, they were about inspiring an entire generation to reach beyond what seemed possible. Before humans could land on the moon, they needed to learn how to survive in space. NASA, the newly formed National Aeronautics and Space Administration, launched Project Mercury. The goal was simple but critical: send a human into orbit around Earth and ensure they could return safely. The early Mercury missions tested life support systems, spacecraft controls, and emergency procedures. Astronauts like Alan Shepard and John Glenn became household names. Their courage was extraordinary. They faced unknown dangers, from equipment malfunctions to the simple physical challenges of weightlessness. Every mission brought new lessons, new discoveries, and new stories to tell. The world followed every launch with awe, witnessing humanity taking its first real steps beyond the confines of Earth. After Mercury, NASA moved to Project Gemini, a more ambitious program designed to prepare astronauts for lunar missions. Gemini introduced long-duration flights, spacewalks, and orbital rendezvous maneuvers. These missions were technically demanding and dangerous. Astronauts spent hours outside their spacecraft, tethered only by thin cables, maneuvering carefully to test how humans could operate in the vacuum of space. Gemini showed that humans could live and work in orbit for weeks, that spacecraft could meet and dock in space, and that the dreams of a moon landing were possible. The program combined precision engineering with human bravery in ways the world had never seen before. Finally, all of these efforts led to the Apollo program, NASA's most ambitious mission yet. Apollo was about more than just reaching the moon. It was about proving that humanity could travel to another world, explore it, and return safely. The program involved thousands of people, engineers designing rockets, scientists studying lunar geology, technicians assembling spacecraft, and astronauts training for every imaginable scenario. Apollo's missions were carefully planned to balance risk with opportunity. Every detail, from the trajectory of the spacecraft to the composition of the astronauts' food, was meticulously considered. This was not just a technological achievement, it was a human triumph. The first manned Apollo mission, Apollo 7, tested the command module in orbit around Earth. Following that, Apollo 8 achieved a milestone no one had imagined just a decade earlier. Humans orbited the moon for the first time. Astronauts saw the lunar surface up close, witnessing craters, valleys, and mountains that had only been studied from afar. The view changed everything. Seeing Earth from space, a fragile blue planet hanging in the vast darkness, inspired a new perspective on life, humanity, and our place in the universe. It was awe-inspiring, humbling, and exhilarating all at once. Apollo 11, of course, is the mission that captured the imagination of the world. On July 20, 1969, Neil Armstrong stepped onto the lunar surface and uttered words that would echo across generations. That's one small step for man, one giant leap for mankind. Buzz Aldrin joined him soon after, exploring the moon's surface, collecting samples, and documenting the experience. Michael Collins remained in orbit, piloting the command module and witnessing history from above. The mission lasted just over 8 days, yet its impact has lasted decades. Humans had traveled beyond Earth, walked on another world, and returned with knowledge and experience that would shape the future of space exploration. Apollo 11 represented the culmination of centuries of observation, decades of experimentation, and years of courage, planning, and determination. After the incredible success of Apollo 11, the world watched eagerly as subsequent missions pushed further into the lunar frontier. Apollo 12, launched later in 1969, demonstrated how precise landing technology had become. Astronauts Charles Pete Conrad and Alan Bean touched down within walking distance of their targeted site, showing that humans could land on the moon with remarkable accuracy. They explored the lunar surface, collected rocks, and even visited remnants of unmanned missions that had landed earlier. Every sample and photograph brought new knowledge about the moon's composition and history. Scientists began to understand that the moon wasn't just a lifeless rock, it was a world shaped by billions of years of cosmic events, including volcanic activity and asteroid impacts. Apollo 13, launched in 1970, became legendary not for its success, but for the courage and ingenuity that saved it. An oxygen tank exploded while the spacecraft was en route to the moon, putting the lives of astronauts Jim Lovell, Jack Swigert, and Fred Haise at extreme risk. What followed was a tense struggle between the crew and mission control back on Earth. Engineers improvised solutions to conserve power, remove carbon dioxide, and safely guide the spacecraft home. The crisis was resolved successfully, and the astronauts returned to Earth, proving that human ingenuity and teamwork could overcome even life-threatening challenges in space. Apollo 13 remains a testament to the resilience, resourcefulness, and courage required for space exploration. Apollo 14 through Apollo 17 continued to expand our understanding of the Moon. Apollo 14 explored the Fra Mauro region, where astronauts gathered rock samples that revealed details about the Moon's ancient geological activity. Apollo 15, Apollo 16, and Apollo 17 introduced the Lunar Roving Vehicle, a small electric car that allowed astronauts to travel farther and carry more equipment. This increased mobility dramatically expanded the areas that could be studied. Each mission revealed new insights about lunar soil, craters, and the history of the solar system. Apollo 17, in December 1972, became the final manned mission to the Moon. Astronaut Harrison Schmitt, a trained geologist, walked on the surface, highlighting the importance of scientific expertise in space exploration. The Apollo program had achieved more than just landing humans on the Moon. It had transformed our understanding of another world and demonstrated the potential of human spaceflight. While the Apollo missions captured the imagination of the public, space exploration was not limited to humans. Robotic spacecraft provided a complementary and crucial perspective. The Soviet lunar program sent robotic landers and orbiters to the Moon, bringing back soil samples and photographs that helped refine our understanding of lunar geology. In the United States, robotic probes explored not only the Moon, but also other planets. Mariners, Voyagers, and Pioneers mapped distant worlds, measuring atmospheres, magnetic fields, and radiation belts. These robotic missions laid the foundation for the next phase of exploration missions that would venture far beyond the Moon into the outer solar system. As space agencies refined their technology, the focus shifted toward longer-term human habitation and international collaboration. Skylab, launched in the early 1970s by NASA, tested how humans could live and work in orbit for extended periods. Astronauts conducted experiments in biology, materials science, and astronomy, learning how microgravity affected the human body. These experiences would become critical for planning missions to Mars and beyond. Meanwhile, the Soviet Union launched satellite stations, and later Mir, pushing the boundaries of life in orbit. These early stations showed that humans could survive, conduct research, and adapt to the unique challenges of living in space. The experiments performed in these orbiting laboratories provided knowledge about nutrition, exercise, and radiation protection lessons that remain central to human spaceflight today. By the late 1970s and early 1980s, space exploration had become a global endeavor. Europe, Japan, and Canada began contributing scientific instruments and technology to orbital missions. The United States launched the Space Shuttle, a reusable spacecraft designed to carry astronauts and cargo into low Earth orbit. The shuttle program represented a shift in philosophy. Space was no longer just a series of one-off missions, but a place where humans could operate regularly. Shuttles deployed satellites, serviced telescopes, and even built parts of future space stations. They symbolized the maturation of space technology, showing that humans could not only visit space, but also return safely, carry heavy equipment, and establish a lasting presence in orbit. As humans spent more time in space, we learned that life beyond Earth is far from easy. Long-duration missions tested the limits of the human body, mind, and spirit. Muscles weaken without gravity to work against, bones lose density, and the heart and other organs adapt in ways that can create health challenges. Astronauts on Mir, Skylab, and later the International Space Station experienced these effects firsthand. They learned how to exercise in space, monitor their nutrition, and maintain mental health while orbiting hundreds of kilometers above Earth. These lessons were crucial not just for surviving in orbit, but for preparing for missions to planets like Mars, where travel times stretch into months or even years. Long-duration spaceflight became a proving ground for human endurance, teamwork, and ingenuity, showing that life in space is not just about technology, it is about adapting humanity itself to the cosmos. Meanwhile, robotic missions continued to expand our understanding of the solar system. Spacecraft such as Near Shoemaker, Hayabusa, and OSIRIS-REx traveled to asteroids, mapping their surfaces and even returning samples to Earth. These missions teach us about the origins of the solar system, revealing how planets formed and how materials like water and organic molecules were distributed. Comets, too, became objects of fascination. The European Space Agency's Rosetta mission orbited and landed a probe on Comet 67P/Churyumov-Gerasimenko, capturing images of a frozen world that has traveled billions of kilometers through space. These robotic explorers provide not only scientific data but also inspiration, showing humanity that even the smallest celestial bodies hold stories billions of years old. Exploration of the outer planets has also revealed wonders beyond imagination. Voyager, Galileo, and Cassini spacecraft sent back incredible images of gas giants, icy moons, and enormous ring systems. Jupiter's moon Europa and Saturn's moon Enceladus emerged as potential locations for extraterrestrial life, thanks to evidence of subsurface oceans beneath icy crusts. The idea that life could exist beyond Earth is no longer science fiction, it is a scientific question, grounded in careful observation and experimentation. Each discovery sparks curiosity and drives the next generation of missions, keeping the spirit of exploration alive. As humans and robots pushed outward, we began to think about returning to the moon and eventually going beyond. NASA Artemis program aims to land astronauts on the lunar surface once again, this time with an eye toward long-term exploration and habitation. The moon is not just a destination, it is a training ground, a laboratory, and a stepping stone to Mars and beyond. Technologies developed for lunar missions like reusable landers, in-situ resource utilization, and sustainable habitats will shape the future of human spaceflight. International partners and private companies are playing an increasing role, making the vision of a permanent lunar presence a realistic goal for the near future. The idea of exploring Mars has captivated humanity for decades. Plans for human missions to the Red Planet are becoming more concrete. Astronauts will face unprecedented challenges, traveling for months through deep space, landing safely on a world with only one-third of Earth's gravity, and surviving extreme temperatures and radiation. Robotic missions like Perseverance, the Mars Reconnaissance Orbiter, and the Ingenuity helicopter have already laid the groundwork. They study terrain, analyze rocks, and even demonstrate technologies like powered flight in the thin Martian atmosphere. Every piece of data helps scientists plan how humans might live, work, and thrive on Mars in the coming decades. Beyond Mars, the solar system holds endless possibilities. Missions to Jupiter, Saturn, Uranus, Neptune, and their moons continue to reveal new worlds, each with unique features and potential mysteries. Probes like New Horizons, which flew past Pluto and the Kuiper Belt, remind us that even the farthest reaches of the solar system are within reach. As technology advances, the line between what is impossible and possible shifts. What once seemed like science fiction, humans traveling to other worlds, rovers exploring alien surfaces, spacecraft reaching interstellar space has become reality. Space exploration challenges our imagination, testing our courage and creativity at every step. Throughout all of these missions, one truth becomes clear: space exploration is about more than science and technology. It is about curiosity, wonder, and the human desire to know what lies beyond the horizon. Each discovery, whether by humans or robots, reshapes our understanding of the universe and our place within it. We study distant planets, moons, and asteroids not only to understand them but to understand ourselves. Space teaches patience, ingenuity, and resilience. It reminds us that our planet is small, fragile, and unique, inspiring efforts to care for it as we look outward to the stars. Looking forward, the future of space exploration is both thrilling and challenging. Humans are preparing for missions that will take us farther than ever before. Mars is the next big goal, but even more distant worlds like the icy moons of Jupiter and Saturn hold secrets we have yet to uncover. Scientists imagine sending robotic probes into the atmospheres of gas giants, exploring the oceans beneath icy crusts, and perhaps even seeking signs of life on moons like Europa or Titan. The solar system is a vast laboratory, and each mission provides data that helps us plan for future human presence beyond Earth. Emerging technologies are transforming what is possible. Advanced propulsion systems, such as ion engines and solar sails, allow spacecraft to travel faster and farther while using less fuel. Reusable rockets, pioneered by private companies, are dramatically reducing the cost of launching into space. Artificial intelligence and robotics increasingly assist humans, performing tasks that would be dangerous or impossible otherwise. Space habitats are being designed to provide sustainable living conditions for astronauts, with recycled air and water, artificial gravity experiments, and advanced shielding against cosmic radiation. These innovations are not just futuristic, they are already shaping the way we explore the cosmos. The dream of colonizing other worlds is slowly taking shape. Concepts for moon bases, Mars colonies, and orbital habitats are no longer confined to science fiction. Engineers and scientists are studying how to grow food in space, build durable structures with local materials, and create communities that can thrive in alien environments. The challenges are immense: protecting humans from radiation, maintaining life support systems, and creating environments that support both physical and mental health. Yet every experiment, every prototype, brings us closer to turning these visions into reality. The very idea of humans living and working on another world is both awe-inspiring and a testament to the resilience of human curiosity. Beyond the technical achievements, space exploration has a profound cultural and philosophical impact. Seeing Earth from orbit changes perspective. Astronauts often describe the overview effect, a profound realization of the planet's fragility and interconnectedness. From space, borders disappear, oceans and deserts blend into patterns of color, and the Earth appears as a small, delicate sphere floating in the vast darkness. This perspective inspires not only scientists and engineers, but also artists, writers, and everyday people. Space exploration reminds us of our shared humanity, our responsibility to protect our planet, and the limitless potential of our imagination. Moreover, space exploration inspires education and innovation. Students around the world dream of becoming astronauts, engineers, and scientists. Every launch, rover landing, or telescope image sparks curiosity and encourages learning in math, physics, biology, and computer science. The discoveries made in space often have practical applications on Earth, from satellite communications and GPS to medical technologies and climate monitoring. Space exploration challenges humans to think creatively, solve complex problems, and collaborate across borders. It demonstrates that when we dare to dream, we can achieve what once seemed impossible. As segment 1 comes to a close, it is clear that space exploration is a journey that combines courage, curiosity, and human ingenuity. From the earliest astronomers to the first astronauts on the moon, from robotic explorers on distant planets to the engineers building the next generation of spacecraft, every step has been part of a grand story. It is a story of discovery, perseverance, and wonder. The journey is far from over. Each mission, each experiment, Each glance into the night sky reminds us that the universe is vast, full of mysteries, and waiting to be explored. And as we continue to each mission, each experiment, each glance into the night sky reminds us that the universe is vast, full of mysteries, and waiting to be explored. And as we continue to reach for the stars, we carry with us the knowledge, imagination, and spirit of every human who has dared to dream beyond Earth. Segment 1 ends here, capturing humanity's journey from early stargazing to the dawn of a future filled with interplanetary exploration, technological innovation, and the enduring wonder of the cosmos. Humanity's exploration of space did not stop at the Moon or Mars. Even as astronauts walked on distant worlds, robotic missions ventured farther, revealing secrets that were previously unimaginable. The outer planets Jupiter, Saturn, Uranus, and Neptune were once little more than blurry points of light in telescopes, but with carefully designed spacecraft, engineers and scientists transformed these distant dots into complex worlds filled with moons, storms, rings, and magnetic fields that defied imagination. The Voyager missions, launched in the late 1970s, were among the first to carry humanity into the outer solar system. Voyager 1 and Voyager 2 traveled billions of kilometers, passing by Jupiter and Saturn and sending back images of swirling storms, massive rings, and dozens of moons, each with its own story to tell. For the first time, humans could see Titan, Enceladus, and Europa up close, revealing features that would shape scientific understanding for decades. Voyager's journey did not end with these planets. Continuing outward, the probes crossed the heliopause and entered interstellar space, carrying golden records with sounds and images of Earth, a message in a bottle to the stars, a symbol of human curiosity and hope. Jupiter, the largest planet in the solar system, proved to be a treasure trove of discoveries. The Galileo mission, which orbited Jupiter for years, revealed volcanic activity on Io, one of its moons, and the possibility of a subsurface ocean on Europa. Scientists began to realize that moons, not just planets, could host conditions suitable for life. The immense magnetic fields around Jupiter created spectacular auroras, and intense radiation belts presented new challenges for both robotic and future human exploration. Every observation brought new questions, illustrating that even a single planet could be the solar system in miniature, with complex interactions among its moons, rings, and atmosphere. Saturn offered its own marvels. The Cassini-Huygens mission, a joint effort by NASA, ESA, and the Italian Space Agency, provided unprecedented insight into Saturn and its system of moons. Cassini orbited the planet for over a decade, capturing images of the planet's icy rings, swirling storms, and enigmatic hexagonal jet stream at its north pole. Huygens, a probe carried by Cassini, descended through the thick atmosphere of Titan, revealing rivers, lakes, and landscapes made of liquid methane and ethane. These observations challenged our understanding of where and how life could exist, showing that chemistry, energy, and liquid fundamental ingredients for life can exist in places far different from Earth. Cassini also studied Enceladus, detecting geysers of water shooting into space from its icy crust, hinting at an ocean beneath the surface. These discoveries emphasize that exploration is not about what is expected but what is possible. Even Uranus and Neptune, the ice giants, became subjects of robotic study. Voyager 2 provided the first close-up images of these distant worlds, revealing blue-green atmospheres, mysterious magnetic fields, and a collection of small moons and faint rings. These planets demonstrated that the solar system was more diverse than previously imagined. Far from the warmth of the sun, they hold clues about planetary formation, the behavior of gases and ices in extreme conditions, and the dynamic forces that shape worlds over billions of years. Each mission taught humanity to expect the unexpected and to value patience and persistence in exploring the cosmos. Closer to home, asteroids and comets emerged as important targets for robotic missions. These small bodies, often no more than a few kilometers across, contain clues to the early solar system. Missions like Near Shoemaker visited the asteroid Eros, mapping its surface and studying its composition, revealing that asteroids are not inert rocks but dynamic objects with their own geological histories. Japan's Hayabusa and Hayabusa 2 missions demonstrated remarkable precision, landing on asteroids and returning samples to Earth, a technological achievement that required engineering ingenuity and meticulous planning. NASA OSIRIS-REx followed with a similar mission to Bennu, returning pieces of an ancient asteroid that could hold organic compounds, offering insight into the building blocks of life itself. Comets, too, became key targets for exploration. The European Space Agency's Rosetta mission and its Philae lander descended onto Comet 67P/Churyumov-Gerasimenko, taking measurements, photographs, and even analyzing the surface chemistry. Comets, which spend most of their time in the cold reaches of the solar system, are ancient remnants of its formation. By studying them, scientists learn about the materials that coalesced to form planets, moons, and even the organic molecules that may have seeded life on Earth. The missions to comets and asteroids illustrate an important principle of space exploration. Even the smallest and most distant objects hold vast potential for discovery. The outer solar system is not the only frontier for robotic exploration. The Sun, the source of all energy in our solar system, has also been studied by advanced spacecraft. The Parker Solar Probe, launched in 2018, travels closer to the Sun than any previous mission, measuring solar wind, magnetic fields, and energetic particles. These observations help scientists understand space weather, which affects satellites, communications, and even power grids on Earth. Observing the Sun in real time allows humans to better predict solar storms and protect the technology and infrastructure we rely on daily. Beyond robotic missions, plans for human exploration of the outer solar system are already being imagined. While crewed missions to Jupiter or Saturn are far in the future, robotic precursors pave the way. Every data point, every image, and every measurement informs future designs for spacecraft, habitats, and life support systems. Scientists study radiation shielding, propulsion methods, and long-term sustainability, ensuring that when humans finally reach these distant worlds, they are prepared for the challenges that await. Even as robots explore distant planets and moons, humans continue to advance in low Earth orbit and on the Moon. Experiments conducted on the International Space Station help us understand how to live and work in microgravity for long periods. These lessons are essential for preparing crews for long journeys to Mars and eventually to asteroids or even the moons of Jupiter and Saturn. Technologies like closed-loop life support, advanced exercise regimes, and remote robotic assistance are already being tested, ensuring that when humans travel deeper into space, survival is possible and scientific productivity is maximized. Space exploration, whether by humans or robots, teaches lessons that go beyond science. It inspires creativity, problem-solving, and cooperation across nations. It reminds us of the fragility of our planet and the extraordinary achievements possible when humanity dares to dream. Each mission, from the smallest asteroid probe to the most complex outer planet orbiter, is a step toward understanding not just the universe, but ourselves. The outer solar system is no longer unreachable. Through courage, ingenuity, and curiosity, humans and machines together are beginning to unlock the secrets of worlds once only imagined. Beyond the traditional planets, humanity has turned its attention to smaller worlds, dwarf planets, and objects in the outer solar system. Pluto, once considered the ninth planet, became the focus of a historic mission in 2015 when NASA New Horizons spacecraft flew past it. For the first time, humans saw Pluto's surface up close. Icy mountains, vast plains, and mysterious formations nicknamed Sputnik Planitia. Pluto's atmosphere, thin yet dynamic, revealed winds and seasonal changes that surprised scientists. The mission also captured images of Charon, Pluto's largest moon, revealing cliffs, canyons, and craters that told a story of complex geological history. These discoveries demonstrated that even distant, tiny worlds can be surprisingly active and diverse. Following New Horizons, scientists began exploring the Kuiper Belt, a region filled with icy bodies beyond Neptune. Each new object in this region provides insight into the formation of the solar system, helping humans understand the processes that shaped Earth, Mars, and other planets billions of years ago. Closer to the inner solar system, the dwarf planet Ceres in the asteroid belt has also captured attention. The Dawn mission studied Ceres for years, revealing a world covered in ice, salts, and mysterious bright spots. Some of these spots are thought to be deposits of salt left behind by briny water seeping through the surface. Observing Ceres challenges assumptions about where water and potentially life-friendly conditions might exist, showing that even small worlds can teach big lessons. Dwarf planets and asteroids highlight a critical lesson of space exploration. Size does not determine significance. Every celestial body has a story, and every story contributes to the greater understanding of our solar system's history and potential for life. While robotic missions explore the solar system, astronomers have turned their gaze even farther, searching for planets around other stars. These exoplanets, as they are called, number in the tens of thousands and vary widely in size, composition, and orbit. Some are massive gas giants orbiting close to their stars, while others are rocky worlds in what scientists call the habitable zone, where liquid water might exist. Discovering exoplanets has transformed humanity's understanding of its place in the universe. It suggests that planets are common, and potentially life-bearing worlds could exist in countless star systems. Missions like Kepler and TESS have revolutionized the search, using precise measurements of starlight to detect tiny dips caused by planets passing in front of their stars. Each new exoplanet expands the imagination, showing that Earth is just one of many possible worlds, and the universe is far larger and more diverse than anyone could have predicted. Emerging technologies are pushing the limits of what is possible in both robotic and human exploration. Advanced propulsion systems, including nuclear thermal rockets and ion drives, could allow spacecraft to travel faster and farther than ever before. Solar sails, which use sunlight to propel spacecraft without fuel, are being tested for long-duration missions. Meanwhile, artificial intelligence assists in autonomous navigation, decision-making, and data collection for robotic explorers, enabling missions to operate in real time even when communications take hours or days to reach Earth. These technologies are not merely incremental, they have the potential to fundamentally change humanity's approach to exploring the solar system. In addition to propulsion and AI, new habitat designs are being developed to support humans on long-duration missions. Concepts include inflatable modules, underground lunar bases, and Martian habitats made from locally sourced materials. These structures must protect against radiation, extreme temperatures, and microgravity effects while providing a livable environment for crews. Scientists are also developing closed-loop life support systems, recycling air, water, and even food to sustain astronauts for months or years. Experiments on the International Space Station help test these systems, while analog environments on Earth, such as desert habitats and underwater laboratories, simulate the challenges of living on other worlds. The search for life has become one of the most powerful driving forces behind modern space exploration. For centuries, humans have wondered whether we are alone in the universe. Today, that question is no longer just philosophical, it is scientific. Robotic missions are specifically designed to look for biosignatures, which are chemical or physical signs that life may exist or may have existed in the past. On Mars, rovers drill into ancient rocks that were once part of riverbeds and lake floors. These rocks may preserve microscopic evidence of past life, Instruments analyze soil samples, searching for organic molecules, complex carbon-based compounds that are the building blocks of life. Each discovery brings us closer to answering one of humanity's greatest questions. But Mars is not the only place where scientists search for life. The icy moons of the outer planets have become prime candidates. Europa, one of Jupiter's moons, appears to have a vast ocean hidden beneath its icy crust. Tidal forces from Jupiter's gravity create heat inside Europa, possibly keeping this ocean liquid. If there is liquid water, energy, and the right chemical ingredients, life could potentially exist there. Similarly, Saturn's moon Enceladus has geysers that shoot water vapor and ice particles into space. These plumes contain organic molecules and salts, suggesting that a warm ocean may lie beneath the surface. Future missions aim to analyze these plumes more closely, perhaps even sending landers or submersible probes to explore beneath the ice. These missions represent the next bold step in the search for extraterrestrial life. Titan, Saturn's largest moon, offers another intriguing possibility. It has lakes and rivers on its surface, but instead of water, they are made of liquid methane and ethane. Titan's thick atmosphere and complex chemistry make it a unique laboratory for studying probiotic chemistry, the processes that may lead to life. Although life on Titan would likely be very different from life on Earth, studying its environment helps scientists understand the range of possibilities for life in the universe. The diversity of environments within our own solar system teaches us that life might adapt to conditions far beyond what we once imagined. Beyond our solar system, the search for life continues through powerful telescopes and advanced instruments. Scientists analyze the atmospheres of distant exoplanets, looking for gases like oxygen, methane, or carbon dioxide in unusual combinations. On Earth, life maintains a delicate balance of gases in our atmosphere. If a distant planet shows similar imbalances, it could suggest biological activity. Telescopes such as the James Webb Space Telescope allow astronomers to study these distant atmospheres in remarkable detail. By analyzing how starlight filters through a planet's atmosphere during transit, scientists can identify the chemical fingerprints of various gases. Each new observation brings us closer to identifying potentially habitable worlds. While robotic missions and telescopes expand our knowledge, engineers and scientists are developing bold concepts for future exploration. One idea involves sending advanced robotic probes to the outer edges of the solar system and beyond. These probes could use nuclear propulsion or advanced ion drives to travel faster and farther than ever before. Some concepts even imagine sending tiny spacecraft propelled by powerful lasers capable of reaching nearby star systems within a human lifetime. Though these ideas remain experimental, they show how far human imagination and engineering have progressed. Human exploration of distant moons and planets remains a long-term ambition. Before astronauts can travel to Europa or Titan, many challenges must be addressed. Radiation near Jupiter is intense, requiring strong shielding. Travel times are long, demanding sustainable life support systems. Communication delays increase with distance, requiring greater autonomy for crews and spacecraft. Despite these challenges, each robotic mission provides critical data that will inform future human journeys. Exploration is a step-by-step process, building knowledge and capability over time. As we push deeper into space, ethical and environmental considerations become increasingly important. Protecting other worlds from contamination is essential. Scientists follow strict planetary protection protocols to prevent Earth microbes from being carried to potentially habitable environments. Preserving the integrity of these worlds ensures that future discoveries are genuine and not influenced by human interference. Similarly, as humans expand activities in space, sustainable practices must guide exploration to prevent the accumulation of space debris and protect orbital environments for future generations. Space exploration also has profound cultural and philosophical implications. Humanity has long been defined by its curiosity and desire to explore. The possibility of discovering life beyond Earth challenges our understanding of biology, philosophy, and the uniqueness of our planet. Missions to the outer planets and interstellar space remind us that the universe is vast and diverse, filled with environments that challenge assumptions about where life can exist. They also emphasize collaboration. Missions like Cassini-Huygens, Rosetta, and the International Space Station involve scientists and engineers from multiple countries, highlighting that space exploration is a shared human endeavor. Exploring the solar system and beyond also strengthens humanity's connection to Earth. Seeing distant moons, planets, and stars emphasizes the fragility and uniqueness of our home planet. From the perspective of space, Earth is a small, delicate sphere floating in darkness. This realization encourages environmental stewardship, global cooperation, and a sense of shared destiny. Each discovery beyond our world enhances our appreciation for life on Earth and reminds us that exploration is about understanding not only other worlds but ourselves. Segment 2 also demonstrates that robotic exploration and future human missions are deeply intertwined. Robots go first, testing environments, collecting data, and revealing hazards. Humans follow, using that knowledge to explore more safely and effectively. Together, they form a partnership that extends our reach, allowing humanity to venture into realms previously thought unreachable. The discoveries made by rovers, orbiters, and telescopes lay the groundwork for ambitious human exploration of Mars, Europa, Titan, and beyond. Each mission teaches lessons about engineering, biology, geology, and the adaptability of life, building a cumulative understanding that shapes the trajectory of space exploration for decades. As segment 2 draws to a close, the story of robotic exploration reminds us that exploration is both a scientific and human endeavor. It is about curiosity, imagination, and perseverance. The outer planets, their moons, comets, asteroids, and distant exoplanets are no longer abstract points of light. They are worlds with unique characteristics, histories, and potential for discovery. By studying them, humans expand knowledge, inspire generations, and push the boundaries of what is possible. The journey from early planetary probes to interstellar mission concepts illustrates the continuity of exploration step by step, mission by mission, curiosity guiding each advance. Ultimately, segment 2 shows that space is not a distant frontier, it is an opportunity for discovery, innovation, and inspiration. Robotic explorers reveal the unknown, test the limits of technology, and prepare humanity for future human missions. They remind us that exploration is a gradual, cumulative process built on ingenuity, courage, and collaboration. Every image sent from a distant moon, every sample returned from an asteroid, and every new exoplanet discovered strengthens the story of humanity reaching beyond the confines of its home planet. The solar system is a neighborhood filled with wonders, mysteries, and possibilities. And beyond it, the stars await, inviting humanity to continue its journey into the unknown. Mars has long captured the human imagination. For centuries, people looked at the red dot in the night sky and wondered if it could harbor life or even civilizations. Today, humanity is on the verge of turning that imagination into reality. Robotic missions have mapped the planet in exquisite detail, revealing deserts, mountains, valleys, and polar ice caps, and providing critical information for future human explorers. Rovers like Spirit, Opportunity, and Curiosity traversed Martian terrain, analyzing rocks, soil, and atmospheric conditions, confirming that water once flowed on the surface. These findings were monumental. They told scientists that Mars was not always the dry, barren planet seen today. It had rivers, lakes, and perhaps oceans in its ancient past. Understanding Mars' history helps humanity answer questions about how planets evolve, why some sustain life, and how humans might one day live on another world. NASA Perseverance rover and China's Tianwen-1 mission continue to expand knowledge of Mars. Perseverance landed in Jezero Crater, an ancient river delta, collecting samples that may one day return to Earth. Janwen-1, which includes both an orbiter and a rover named Zhong, studies surface geology and atmospheric conditions. These missions are not just scientific experiments, they are reconnaissance for human exploration. Each rock analyzed, each terrain mapped, informs engineers about where astronauts could land, where habitats could be built, and how to extract resources from the Martian environment. The concept of in-situ resource utilization using local materials for water, fuel, and building supplies will be critical for sustainable human colonization. Preparing humans for Mars requires more than just landing technology. Mars has a thin atmosphere, composed mostly of carbon dioxide, offering little protection from radiation. Temperatures fluctuate wildly, and dust storms can cover the entire planet for weeks. Astronauts will need habitats that shield them from radiation, provide stable air pressure, and regulate temperature. Life support systems must recycle air, water, and food efficiently, and renewable energy sources such as solar panels or compact nuclear reactors will be necessary to power settlements. Training astronauts for long-duration missions involves not only physical preparation but also psychological readiness. Isolation, confinement, and communication delays with Earth require teams that can operate autonomously while remaining cohesive and resilient. Robotic missions will continue to support human efforts, scouting landing sites, testing equipment, and providing real-time environmental data. Drones, autonomous rovers, and orbital satellites will work together to map hazards, locate water ice, and monitor weather conditions. Even before humans set foot on Mars, robotic explorers are laying the groundwork, ensuring that the first steps taken by astronauts are informed, safe, and productive. This partnership between humans and machines exemplifies the principle of incremental exploration: build knowledge, mitigate risk, and advance capabilities with each mission.